those three scenarios. In Algebra 1 and Algebra 2, when we did systems of equations, we went through the methods of substitution and elimination to solve those systems and working out algebraically how to solve those. We also talked about graphing to solve and all that. So know that those exist. Don't really care if you use those. If you want to do them by hand, that's the way you want to do that. We're going to, in Algebra 2, we taught you that you could use an augmented system with a matrix. So that's the method we're going to use because that's probably what you would all do anyway because you got that nice graphing calculator. So we're going to utilize that technology, make this pretty easy. So we're going to review that a little bit. So idea is just to solve these systems of equations, and let's just start with a nice linear system. Now, keep in mind, I mentioned all those other methods for solving a system. When we do nonlinear systems later on in this chapter, which means they're not, you can't put them in a matrix, and we've got to use those other methods. So those are going to come back up. So you might want to make sure you remember how to do those at some point. But the idea of solving a linear system, we've got a better way. So we're going to use it. And that's using that augmented matrix. And only things that you really need to remember with augmented matrix and matrices to solve systems is that you need them to have the variables all on the same side and to be in the same order. That, you got X's, Y's. If we get a 3-variable system, X, Y, and Z, 4-variable system, get them in alphabetical order, each equation. Get the letters on the left side, plain numbers on the right side. You got to have it that way in order to set up your augmented matrix. And then what was the method that we used? Does anybody remember the little button? It was 4 letters. Okay. Which one of them we were picking? RREF. Reduced row echelon form is what that stood for. That's what we're doing with our augmented matrices. So for this particular system, does anybody remember what size the matrix should be? 2 by 3. Rows by columns. Rows goes first. So there's 2 equations. That's the rows. And the columns, you got an X column, a Y column, and then a numbers column. Okay, so this is 2, 1, 5, -4, 6, -2. So that's our augmented matrix. What you've got here, what makes it an augmented matrix? If I cover this part up, that little 2 by 2 is what's called the coefficient matrix. And then if I cover up these, then that's the solutions matrix out of that. But if you put them together in one, that's called an augmented matrix. That's what it is. But augmented matrix, you can use reduced row echelon form. You can use the calculator to do that. So let's put those in. Just remember how to do that. So second matrix. So the X inverse buttons lit up in red there. Go over to edit and tell it what size the matrix you need. We need a 2 by 3. And then you're just typing in, your values. So 2, enter, 1, enter, 5, enter, -4, enter, 6, -2. Make sure everything is in. If you miss a sign or mistype one part, it will make everything change. Okay, so be careful before you get out of that window. Make sure you got all your stuff in there correctly. Okay. Second, quit to get back to the regular calculator screen, and then we're going second matrix again. We're going to do some math with that matrix now. So press the right arrow key to get to the math portion of the menu. And then we're looking for RREF. It's down toward the bottom, so I'm going to press the up arrow to get down there quicker. And RREF is the 2 R's. If you pick RREF or just REF, it won't completely solve the thing. It'll only get you part of the way. So, and then you just need to tell it which matrix to do that to. So second matrix. I put mine in A and hit enter. And that creates that matrix. Let's So after RREF, we get an augmented matrix that looks like this: 1, 0, 2, and 0, 1, 1. What that tells us is that we have an ordered pair solution 2, 1. Top row is X, bottom row is Y. If you had more variables, obviously it's in alphabetical order, top to bottom. That last column tells you what's going on there. Okay. Do another. 2x plus 3y equals 1. Hang on just a second. I don't know if you want this recorded or not. Okay. I didn't know what he was going to say to me. They were recording something he didn't need. So remember that 20 minutes? All right, so here we have a system. Now, if I'm in Algebra 1 class, I probably do this by substitution, and probably can do it. Just you guys are fairly good at algebra. You can probably do that by substitution if you wanted to. But we're practicing matrix stuff here. So what do we need to do before we can do that? Get all the variables on the same side. So that second equation just needs fixing. So subtract x. So that's going to change that to negative x plus y equals negative 3. Be careful of your signs. Again, when you put that into a matrix, if you miss a sign on any piece of it, it's going to work it a different, and get like it's a different matrix and get you different answers. You won't even get, most likely wouldn't even get one of the answers correct. Okay, so that's our augmented matrix that we need to put in and do our REF to. So, second matrix, edit. I got a 2 by 3 there, bless you. 2, 3, 1, negative 1, 1, negative 3. And then I've already used the RREF function. One of the good things about your calculator is if you just press the up arrow, you can copy and paste that. You guys probably already knew that. If you didn't, now you do. So just press the up arrow until that's the thing you want to copy and paste is highlighted, and then just hit enter, and it'll copy it down to the new line. And that way we don't have to hunt through the menu system to find RREF of A again. And it may have been nice to know earlier, but that's a nice thing. So now, if you put it in a different matrix, if you put yours in B, you would need to go back and delete the A and put the B matrix in there. But here we get X is 2 and Y is negative 1. So 1, 0, 2, 0, 1, negative 1. So we get 2, negative 1 for this ordered pair. So that means if we were to graph these two equations, they would cross at the ordered pair of 2, negative 1. That's what we're finding there. So these were both consistent and independent systems. Look at this system. 2x plus y is equal to 5. 4x minus 8 is equal to negative 2y. So what do you do? Okay, swap some stuff around. What do you want to swap?
Add 8 and put the negative 2 on the left, which makes it positive.
Okay, that works fine. So moving the y over to the left and the 8 over to the right, that works fine. You could also just move the 4x and get that. It's going to work the same either way. If we do what Hunter suggested, that's going to give us this equation: 4x plus 2y is equal to 8, positive 8. And then the other equation is not changing any. If you had just moved the 4x, you could have negative 4x minus 2y is equal to negative 8. either of those works when you do that. Why are those equivalent equations? What's going on there? The top one there is all positives, right? And the bottom one's all negatives. So they're equivalent because everything, if you just divide the second one by -1, you get back to that. So that makes it legal to do. So no matter which way you move things around, even if the signs are different, as long as you're getting X's and Y's on the same side and your process is mathematically legal, it's going to work out okay. So when you set up your system in a matrix, you'd have the 2, 1, 5, and if we do +2, +4, +8, it's going to give us the same solution as if we put -4, -2, -8. Because no matter which way I solve that second one to get the standard form out of it, it works. Okay, so let's run that with the matrix. So second matrix, edit. Tell I'm a little bit bored with it. Probably because I taught this Monday night too. 4, 2, 8. That right numbers. Although it was different examples, so maybe I shouldn't be so bored, but it's boring. So. All right, so this one's a little different. Oh, it doesn't look the same. I did RREF and I got 1, 1/2, 0, and 0, 0, 1 or negative. Yeah, 1. Okay, so what does that tell us? Why? Okay, so that tells us that 0x plus 0y is equal to something other than 0, right? That can't happen, can it? 0 plus 0 is no way going to be anything but 0. So that's correct. This is a no solution. Because we have we have a false statement on that last equation. The reduced system. Okay. So all zeros on the coefficient part and some other number over here. So 1 in this case could be anything really. 1's pretty consistent there though. Zeros and then something else, that's a no solution. If it's all zeros, then what do you think would be? That would be an infinitely many solution situation out of that. So let's look at a system that maybe does that. Just you already know that. 2x plus y equals 4. And I won't even make you do too much work here to get it in the right order. We know second equation, it very easily could be done incorrectly because it almost looks correct in the right order and everything. But the second equation should be -6x minus 3y. And so that's our matrix that we need to put in there. Edit 2, 1, 4, -6, -3, -12. Quit RREF on that, and we see that bottom row has all zeros on it. So 1, 1/2, 2, 0, 0, 0. And again, if I'm changing that to a fraction, if it's a weird looking decimal there, to change that to a fraction in your matrix there, you can just hit math, enter, and it'll convert decimals that are inside of there to fractions, which is what you want to do. You don't want to use a rounded decimal there for answers, especially if we're going to do something with them later. Now, here's the kicker for college algebra when we do infinitely many solutions. In Algebra 1, we just wrote infinitely many solutions. In Algebra 2, that's what we did. in college algebra, we've got to take that and say, okay, there's infinitely many solutions, but they're of a certain kind. So this is an infinitely many solutions situation. But they're of a certain kind. The kind that they are built off of this equation. Excuse me. All right, so that top row can be pulled back out as an equation. The ordered pairs for all of these solutions to this can be built either in terms of x or in terms of y. In terms of y, what that means is your ordered pair is going to be some expression for x, and then we're going to pick a y value to start with. So like if we picked y was 2, we could get the x value that goes with that. Okay, so we're going to find it in terms of y. So that means I need to get this equation to have an expression for x that has y's in it. So that just means get x by itself. So we know we would subtract 1/2 y and then get negative 1/2 y plus 2. That's in terms of y. But it also could be in terms of x. And in terms of x means x is your one you're picking, and you're going to get the y values out of that. So we need to solve this equation for y to get it, so we get something that's got x's in it. So we would subtract x and then multiply by 2, so that'd be 2x, negative 2x plus 4. And I'll tell you which, in terms of what variable to deal with on that. But that's the extension of this from doing it a little bit differently than we did it in Algebra 2 and Algebra 1. So that's where it kind of starts getting a little tougher, a little more interesting maybe. Okay. So if I say in terms of y, that means y should be the only variable that's in there. If I say in terms of x, that means x should be the only variable in there. So we want to be able to write those in that form. All right. So 2 variable systems, 2x3, augmented matrix, or REF, and we've seen a situation with all of the possibilities. Let's look at this system: x plus y minus z equals -1, 4x minus 3y plus 2z is equal to 16, 2x minus 2y minus 3z is equal to 5. So a 3 variable system with 3 equations. And again, the same rules apply. There can be one solution, no solutions, or infinitely many solutions. So all those things can still happen here with this. 3 variable systems, what we're dealing with are planes, like not zoom planes, but planes like flat surfaces. And a good example of a one solution 3 variable system would be like this corner up here. Like that one small point is the solution to where this wall meets that wall meets the ceiling. 3 flat planes, when they cross at one point, it's like a corner of a room. And so that's what we're dealing with. That's what these equations build, are flat planes, if you were to graph them in 3D out of that. Now, infinitely many solutions in 3D could be a lot of different things. You could have 2 planes that smack together, or 3 planes that all line up and are exact same plane, or you could have 3 planes that meet on a line. So like you might have here's a plane, here's another plane. That's 2 planes meeting on a line where the 2 pages come together, and then maybe you stick another one in there like a book, and they're all 3 meeting on that line where the papers are touching. So that's an infinitely many solutions situation. So that's where the rewriting the equations can be useful. All of that. So I just disordered my notes here. I'll put it back together. All right. So augmented matrix, what size should this one be? 3 by 4. 3 equations. That's 3 rows. 4 columns, X, Y, Z numbers. Okay. 1, 1, -1, -1, 4, -3, 2, 16, 2, -2, -3, 5. So that's what the matrix should look like that we're putting in. Second matrix, edit. I'm going to use matrix A again because it doesn't matter. 3 by 4, -1, -1, 4, -3, 2, 16. Everything's good. REF. Get that matrix as a solution. So that there tells us that X is 2, Y is -2, and Z is 1. So we get an ordered triple. 2, -2, 1. Definitely much better than doing those by hand. If you had me for Algebra 2, you probably did some of them by hand.
Are we going to go back over that process?
What process? Of doing it by hand? No, you won't have to do linear. The non-linear systems won't be in 3 variable. Just because you guys have not experienced 3D parabolas. No, calculus is the perfect time to start when you do that. Because there's a lot happens when you to get a 3D parabola or it's a rotated parabola, and there's some calculus that has to happen to rotate it like that to get that headlight shape that creates. It's an interesting thing, but there's some calculus that has to happen for that. We're not there yet. All right, let's look at another one. 2x plus y minus z equals -2. X plus 2y minus z equals -9. X minus 4y plus z equals 1. Again, 3 by 4. Make sure everything's in order. It is in this one, but when you go to do practice with this, you got to just make sure stuff's in the right order, because this textbook's kind of notorious for just swapping one little thing, and if you don't pay attention, you've worked it and you will not get the same answer. Okay. Well, why not put an X there? That's a 1. All right. And through our REF, true it, I'm going to copy it, paste it. That's what I'm going to do. Second matrix, edit. 2, 1, -1. You guys are much faster putting these in than I am, because you get to use your thumbs. You have to click one thing at a time. And then 1, -4, 1. All right. REF on that. And I'm going to hit math, enter, so I get fractions on that. Just like I thought, 0.3 repeating was 1/3. So that's good news. But what's going on with this one? No solution. Yikes. That right there says no solution. Remember that the math word for that is inconsistent. So make sure you remember that too. Okay. Do another. Example G. X minus 2y minus z equals 8. If there's a missing piece, what do you put in the place of it? 0. If there were a missing variable in one of the equations, then make sure you put a 0 there. Sean? No solution. They can't have terms. There's nothing to make in that. Be patient, grasshopper. Or I will give you one that has that to do. Maybe this. Okay, so we got a system. This happens to have bigger numbers in it. Not that that makes any difference as far as the likelihood of infinitely many solutions or no solution or anything like that. Just makes two-digit numbers are funner. That's not more fun than single-digit numbers. Right? So set up your system. 1, -2, -1, 8, -3, 1, 23, 5, -4, -5, 5. All right, so put that system into the old calculator. And matrix, edit, 3 by 4, 1, -2, 1, oops, -1, 8, 2, -3, 1, 23. All right, so here we go. RREF on that. Let's go through the process of getting it in again the old-fashioned way. What you got? Infinitely many solutions. See that bottom row is all zeros. So that tells us this is infinitely many solutions. So that bottom row tells you what's going on if there's infinitely many solutions. So infinitely many solutions. We can abbreviate that IMS if you want to. As you're doing your practice or on the quiz and stuff. IMS is fine. Also, remember that means consistent and dependent. Now, here's where we got to do in terms of, because it's infinitely many solutions. That's where we got to do that. So let's do this one in terms of Z. Okay. So that means when I get done, I'm going to have an ordered triple, and it's going to only have Z's in the equation or in the expressions. Okay, so I'm going to have an expression for X, an expression for Y, and then Z is just the plain variable. Okay, so we've got to take our matrix after doing RREF and look at the equations that it has. So X plus 0Y plus 5Z is equal to 22. And then the next equation is Y plus 3Z is equal to 7.
I could have been a pen, please. I brought it back today.
Oh, it's okay. Thank you. I never known it was gone. So X plus 5Z is equal to 22. So that's not too difficult to get in terms of Z, which means get X by itself. That's what we're trying to do. Get X by itself. So that's one step. Subtract 5Z. So X is equal to -5Z plus 22. So that's what's going to go up here in our order triple. The next equation tells us, it's got Y and 3Z plus 3Z is equal to 7. We want to get y in terms of z, so we just need to get y by itself. So move it. Y is equal to negative 3z plus 7. Look at every expression. The only variable that's showing up is z. Okay. If there happened to be one of the other variables, then you've got to do a little bit of substitution to get only one variable in your solutions. Okay. And on 3 variable systems, the most common thing that I'm going to ask you for is in terms of z. I think your textbook's pretty consistent with that as well. All right. All right, so that's solving systems. Let's put an application of that. Remember back when we were doing the chapter on quadratics, and we only did, we had the graph, and we asked you to write the equation of that quadratic. And we only did the ones that had the vertex and one other point, and we skipped the other ones that just had 3 random points. Well, this is where we go back and get those kind of problems out of that. So let's get an application of systems of equations. Take 3 points or 3 ordered pairs. Take 3 ordered pairs from a quadratic and create a function using systems of equations. All right. I'm not going to draw a graph. I'm just going to give you some points. Points on a quadratic. So remember that section, they would have a graph drawn, and you would see 3 ordered pairs marked. Those ordered pairs might be -4, 1, -4, 1, 6, and 3, 0. Okay. 1 happens to be an x-intercept. That really doesn't matter. Okay. Now, from there, we've got to take those ordered pairs and build some equations from those. And we've got to remember standard form for a quadratic. What's standard form for a quadratic? Did somebody say ax squared plus bx plus c? Standard form for a quadratic. Okay. So every ordered pair, we can build an equation with the x and the y. Okay. So your first equation that comes from the ordered pair -1, -4, that equation is going to be a times -1 squared plus b times -1 plus c is equal to -4. And then you can, convert that into a nice, equation. A minus b plus c is equal to -4. And then same thing for 1, 6. You're going to have a times 1 squared plus b times 1 plus c is equal to 6. And you convert that into a nice equation. 1 squared is 1, so that's 1a plus 1b plus c is equal to 6. And then the last one, 3, 0. So you convert that over, you got a times 3 squared plus b times 3 plus c is equal to 0. And you convert that over into a nice equation. That'd be 9a plus 3b plus c is equal to 0. Well, this over here is a 3 variable system of equations that we can solve for a, b, and c. If we solve it for a, b, and c, we'll have the coefficients for our standard form of a parabola. That's what we're doing with this. We're building a parabola. We're finding the coefficients for the standard form of a parabola using this system of equations. So that augmented matrix would be 1, -1, 1, -4, 1, 1, 1, 6, 9, 3, 1, 0. Okay, and that's what we want to run with our calculator on. Second matrix, edit. So 1, -1, 1, -4, 6, 9, 3, 1, 0. And then I'm doing RREF on that. And that tells me that A, B, and C this tells me I have an answer, and A, B, and C should be -2, 5, and 3. So my quadratic would be f of x is equal to -2 x squared plus 5x plus 3. So finding the equation for a quadratic using systems of equations. That's what you're doing. So you're going to build standard form based on that. From there, you would be able to, if we were doing more quadratic stuff here, you could find the vertex, axis of symmetry, all of that stuff that goes along with that. You get exact values for that. So nice application of 3 variable systems there, going into something that we've actually done before. All right, one other thing for these 2 sections that we'll talk about, and that is row operations. And this is a non-calculator thing. So row operations, we did this in Algebra 2, I believe, or my Algebra 2 classes did. It's where you take a matrix. It really doesn't matter what size the matrix is or anything like that. It's not coming from a system of equations. It's just a matrix that they just give you the matrix. We'll do this one. 1, -2, 2, 0, 1, 3. They give you this matrix, and then they say, perform this row operation. 2 times row 2 plus row 1 equals row 1. What this tells us to do is to take row 2 and double it, add that to the row 1, but only change row 1. Row 2 in our answer should be the exact same thing that it is here. Whatever it's equal to, that's the one that's changing. Okay, so row 1 is the only one that's changing. So when we do that row operation, I can go ahead and copy down row 2 because I know it's not changing because it says it's equal to row 1. Okay, so you're only going to change that row. So we're doubling row 2 and adding it to row 1. So 2 times 0, still 0, plus 1, still 1. 2 times 1 is 2, plus -2, 0. 2 times 3, 6, plus 2 is 8. This is the answer. You've done that row operation. That's all you're doing. Now, when we do RREF with your calculator, what it's doing when you put a system of equations in there is it's doing all of the correct row operations to end up making the system look like that. Sometimes it's more than others. And if you go into engineering, you might take a linear algebra class, and you may have to actually manually do the row operations by hand and show every step there. But I'll let you enjoy that when that time comes, because it's long and tedious, and sometimes your neighbor will take 3 steps and you'll take 22 steps to do that. It's depending on what route you take. let's take another matrix here. 2, -4, 9, 5, 3, -7. Now, we kind of think that may have came from a two-variable system, but it really doesn't matter. You can take any matrix of any size and do row operations with it. It doesn't matter where it comes from. Okay, so for this one, we're going to do 2 row operations. Okay, so row operation number 1 is going to be row 1 is equal to -3 row 2 plus row 1. And then row operation number 2 is row 2 is equal to 5 times row 1 plus row 2. Okay. So, and I know in your textbook, in the practice, you're going to have to do successive row operations. So when you do these, just do in order and then use the answer from number 1 to do the next part. Okay. So for the first row operation, what row is changing? The first row. That's the only one that's changing. There's some stuff done with the others with the second row, but you're not changing it. So when I work out number 1, my solution should have 5, 3, -7 still in the second row. I know that's not changing. Okay, I just need to find out what row 1 is going to be. So -3 times row 2 plus row 1. So -3 times 5 is -15 plus 2 be -13. Okay, and then -3 times 3 is -9 plus -4, -13 again. -3 times -7 is 21, plus 9 is 30. So after row operation number 1, this is my matrix.
Shouldn't that be?
-3 times -7 is positive 21, plus 9 is 30. All right. Operation number 2, what's the only one that's changing? Row 2. So I'm going to copy down my row 1. Okay. And then do the work after that. Okay. That is, I don't know, it's not you don't have to do it that way, but it sure does keep me from screwing things up. All right. So 5 times row 1 plus row 2. So 5 times -13. -65 plus 5 is -60. And then 5 times -13, still -65, plus -13. Or, excuse me, plus positive 3, sorry. 5 times -13 is -65 plus 3. -62, all right? 5 times 30, 150, plus -7, 143. And then that right there is the answer to the whole problem, because you've completed the 2 row operations that they have. If there were a third row operation, you would use this to do the third row operation. So it's a successive in order kind of thing there with those. All right. So first 2 sections of this chapter, not incredibly difficult. 852, 17 through 79, 866, 5 through 87. That'd be your practice problems for this. Okay. Work day is tomorrow, folks that missed the test yesterday. Your test is tomorrow during work day. Derek, are you ready? Or you need a second to breathe?
Quiz?
Yeah.
I'm gonna look over everything.
All right. Tell me when you're ready.